when I provide you a given cross-section, when I provide the EI value, okay, I can ask you to determine the maximum height of this building, okay, which satisfies the stability condition. Okay, so we always have a limited value about the total height. Okay, and when the height is larger than this value, the structure will not satisfy the stability condition. Okay, so now I show you how to obtain the solution for rigid structure. Okay, we consider a very simple column. Okay, and the low support is a pin support, but with a rotational spring. Okay, if there is no rotational spring, okay, the structure, it is impossible to have a column, okay, stand in the vertical direction. Okay, it will becomes a beam. Okay, so we have a resistance. We have a resistance or constraint. Okay, due to the neighboring members, and the influence of the neighboring members can be represented by, okay, a rotational spring. Okay, so here we have a rotational spring, and then, okay, for this vertical column, okay, when the applied force is less than the critical load, how about the structural response? So structural response is always equal to 0. Okay, if this is an elastic member, the response is vertical deflection, right? It is impossible to have a horizontal response because the force is in vertical and the column is also in vertical. So it is impossible to have a horizontal response. So horizontal response occurs only when buckling occurs. Okay, so here we consider a very small disturbance. Please understand, this is a very small disturbance. This rotation angle is any value. Okay, it's a very small disturbance, but you can understand this is a very small disturbance. So, and then this rigid bar has a rotation. Okay, and this rotation makes, okay, the point here, okay, original location here move to this location, a new location, and this column is subject to a vertical force. Okay, so when this point is moved to a new location due to the buckling, okay, we can obtain, okay, the moment equilibrium equation for this new state. Okay, so we can have an equation. Firstly we apply the equilibrium measure. Okay, we first consider a very small rotation displacement. Okay, this represents, okay, a small disturbance. Okay, small disturbance, and due to this small disturbance, we can obtain, okay, the horizontal displacement. Please understand, this displacement is not due to the deformation. This displacement is due to the rotation. Okay, so this displacement actually is the distance from the original location to the new location. So the horizontal distance is equal to A times the sine angle. Okay, the sine phi. This is the sine angle. So this is a horizontal deflection. Okay, when the rotation angle is very small, the sine angle is approximately equal to angle. So please understand this, okay, relation. Okay, when the angle is very small, the sine angle is not equal to 0. Okay, I should provide you this formula in the list. So sine theta or sine phi is equal to theta or phi when this theta or phi is very, very small. Okay, so this is a horizontal displacement, and after obtaining the horizontal displacement, we can take a moment for this point. We can establish a moment equilibrium equation. Okay, so the moment due to the applied force is equal to the applied force times the horizontal distance. Okay, horizontal distance V, and due to the rotation, moment resistance will be produced by this rotational spring. This is a rotational spring, it's not a translational spring. For rotational spring, the spring just provides moment resistance. The moment resistance due to the rotational spring is equal to the stiffness of the spring times the rotation angle. So the moment resistance is equal to K times the rotation angle. Okay, and the moment due to the applied force is equal to the applied force times the horizontal distance. So this is a horizontal distance. So we can obtain the moment equilibrium equation, and we can extract this small rotation angle from the equation. So please tell me, how about the solution to this equation? The solution to this equation, actually we have two solutions. The first solution is the rotation angle phi is equal to 0. Okay, this rotation angle is equal to 0. This is the first solution. This is the first response. Actually, this is a response before bifurcation. Okay, so the response before bifurcation in this special case is equal to 0, but we know this is in the vertical direction. Okay, the response is the vertical direction. If this is a elastic column, the response is not 0, but the response is in the vertical direction. Okay, and also from this equation, from this equation we can obtain second solution. The second solution is we set the terms in the parenthesis equal to 0. Okay, when the term in the parenthesis equal to 0, so we set the term in the parenthesis equal to 0. From this equation, we can obtain the not trivial solution. And this not trivial solution about P is just the critical load. Why? I show you why this is a critical load. Okay, so firstly, I show you why this is a not trivial solution. Because when the term in the parenthesis is equal to 0, the response can be any value, because any not zero value times 0 is equal to 0. So any response can satisfy the equilibrium equation. That means the response can be any value. So this is an unstable response, because response can be 0 or infinite. Okay, and this response means the horizontal response, because this is a rotation, right? So this means the horizontal response. So this is a response after bifurcation, because the direction of response is changed. Original response in the vertical direction, but when the applied force is equal to the critical load, okay, we can have any horizontal response, because we can have any value about the rotation angle which satisfies the equilibrium equation. So the response can be any value. Okay, so that means the structure becomes unstable when P is equal to the critical load, because the direction of the response changed from the original vertical response suddenly to the horizontal response, and we don't have any horizontal force. We just have a vertical force, but horizontal response is produced. If you do the equilibrium analysis, okay, for the vertical member, it is impossible to have a horizontal response. But after bifurcation, after buckling, the horizontal response occurs. But please understand, I want to mention a very important concept. Okay, in the response analysis, we always try to obtain the response. Okay, but when we do the stability analysis, please do not try to obtain the response. As I mentioned, after bifurcation, after buckling, the response can be any value. So the specific value of the response is not meaningful. Okay, because when the structure becomes unstable, the structure can any values of response. Okay, can any values in the response. So please do not try to get a solution about the response. Please just set the coefficient before the response equal to 0, and then the response can be any value. Okay, the response can be any value. So this is a critical load. This is a critical load. Okay, and I will show you, okay, how to determine the structure is stable or unstable. Okay, based on the second derivative, based on the energy method. Okay, so here I show you the concept. Okay, usually when we establish the equilibrium equation, we can obtain two solutions. One is a trivial solution, the other one is a not trivial solution. For the residual structure, the trivial solution must be equal to 0. Okay, must be equal to 0. And the not trivial solution means the solution about applied force. It's not the solution about response. Okay, not trivial solution is a solution about the applied force, and the corresponding response can be any non-zero value. Okay, because any non-zero response can satisfy the equilibrium equation when the applied force is equal to the critical load. Okay, so this is a basic idea I want to tell you very clearly. Okay, and then we can, for the same problem, we can apply the energy method. Okay, so now I show you the energy method. Again, we consider a small rotation, and we have two parts about the potential. The first part is strain energy. The second part is a potential due to the applied force. For the strain energy, the residual bar has no contribution, any contribution to the strain energy, but the rotational spring has a contribution to the strain energy. Okay, so this strain energy is totally from the spring, not from the residual bar. Okay, so here this is the formula to calculate strain energy for any spring. The strain energy for any spring due to rotation or deflection is equal to stiffness of spring times the response of the spring square over 2. For translational spring, the response means the elongation of the spring. Okay, the deflection of the spring or elongation of the spring. But for the rotational spring, the response means the rotation angle, the rotation of the spring. Okay, because this is a rotational spring, definitely this is rotation. So this is a general formula to obtain the strain energy. Okay, and then we try to obtain the potential due to the external force. So please look into here. Okay, the potential energy due to the external force is equal to the negative of the work done by the external force. Okay, so you just need to obtain the work done by the external force and then add a negative sign, that's all. Okay, but when we calculate the work done by the external force, please understand here we do not have coefficients 1 over 2. Why? Because this U is not developed during the application of the applied force, because the force is applied in the vertical direction. So U is in the horizontal, is not due to the application of this force. U is totally due to the rotation. Okay, it's due to the rotation. So this U is not due to this force. This U due to the rotation, so they are independent. So this is a similar to a virtual work. So we don't have a coefficient of 1 over 2. Okay, so this is U is not elastic deformation. This is a change of the vertical levels for the force application point due to the rotation. So here we don't have a coefficient 1 over 2. Please understand this point. Okay, so how about U? U is a vertical distance from here to here, from here to here, due to the rotation. So the vertical distance U, actually is equal to the original length. Okay, the original length minus the distance from here to here. And this distance from here to here is equal to A rho times cosine angle. Okay, so it's equal to A rho minus A rho times cosine angle. So we have a potential energy here. So this is a potential energy. It's equal to A rho minus 1, A rho times parenthesis 1 minus cosine angle. Okay, this is a standard formula. But you have to add the negative sign. Okay, so for any residual bar, when there is a rotation angle equal to theta or phi, the corresponding potential due to this applied force is always equal to this standard formula. Okay, it's always equal to this standard formula. Okay, so we can obtain the total potential. Okay, and the potential due to the compression force is always negative. This term is always negative. It's always negative. Okay, when it becomes positive only when this term is a tension force. When this force is tension force, it is in the opposite direction of U. It becomes positive. Okay, when the force is a compression force, it is always negative. Okay, so please understand another from a different point of view. If the force is a tension force, and the potential due to the applied force is always positive, right? So, and the strain energy is always positive. So positive plus positive, it is impossible to equal to zero.
Yeah.
Okay, so for the structure subject to tension force, there is no instability problem. There is no buckling problem. Okay, so it's very easy to understand because this term is always positive. So the total energy is always positive. So there is no So this is a case. In this case, when the force is a compression force, the second term is negative, and then we can take a force derivative. And when we take a force derivative, usually this is a nonlinear equation about the rotation angle. It's a nonlinear equation, so you have to linearize the equation. How to linearize the equation? For small rotation angles, the sine angle is equal to angle. And how about the cosine angle? When the angle is very small, cosine angle is equal to 1. Okay, so sine angle is equal to angle, cosine angle is equal to 1. Okay, that's all. So we can linearize the equation. When we linearize the equation, we always able to extract the unknown rotation angle from the equation. Okay, so by setting the coefficient term equal to 0, we can obtain the critical load. Okay, so please understand. If you obtain the critical load is a function about the rotation, that means your solution is not correct. The critical load is just a function of the structural behavior. Structural behavior including the stiffness of structure and the length of the structure. Okay, it is impossible. A function of the response. Okay, so the critical load is a structural natural behavior. It is similar to the dynamics issue. The frequency is a natural behavior of structure, and also the critical load is a natural behavior of structure. When you have complete design for a structure, the critical load is already there. Okay, the critical load is already there, like the frequency is already there. When you complete the design, when you have built the building, the frequency is already there. Okay, so the critical load is just a function of the structural properties. It is independent of the response. So if you obtain the critical load, which is a function of the response, that means your solution is not correct. But not so many students can really understand this issue. If you don't believe, I will show you in the end of this the lecture for this subject. Okay, I will show you one example. I will show you why. The critical load is just it's just a function of the structural properties and independent of response. Because in the previous examination, some students make mistake. From this example, it's very easy to understand. The critical load is just a function of the structural properties. But if I provide you more complicated questions, you will make mistake. You will obtain the critical load, which is a function of the response. So we have obtained the critical load, and then you can obtain the second derivative. After obtaining second derivative, because you just need to take a derivative one more time for this equation, so you can obtain the second derivative and then linearize the equation. Linearize equation means you take a cosine angle equal to 1. So we obtain the second derivative, and then you substitute the critical load because we already obtained the critical load. So critical load is equal to K over A load. So when the applied force less than the critical load, that means K minus K over A load, which is larger than 0. When P is less than K A load, if you substitute K critical load here, this term is larger than 0. So the second derivative is positive, that means the structure is stable. When P is larger than the critical load, this second derivative is less than 0, so the structure is unstable. We always have a conclusion like this. It is impossible to have a different conclusion. So we always have a conclusion like this. Okay, but this is just a conclusion for single degree freedom system. For multi-degree freedom system, we have a different description, okay, about the stability issue, okay.